Okay, so 4.4 is on substitution, and it basically is just another way to evaluate an integral. So really quick, I just want to review where we've come from with our different methods of differentiation and then integration. So a differentiation, we had our basic constant rule, so the derivative of any constant is 0. We had our power rule, we had our trig and our exponent rules, we had our product rule, we had our quotient rule, we had our chain rule, and we had implicit differentiation. So we have a lot of different methods. Pretty much for integration, you have your constant rule, you have your power rule. You're going to have your trig rules and your exponent rules. Those don't really change. And then you have substitution. And substitution is the one that we're going to use for our product and our quotient rules. Now, the other thing, we do have one other one that I was just thinking of, and that's called separation of variables. And that one we'll talk about in the next couple weeks here. So that one would be similar to like an implicit. But basically, these are very, very obvious what you need to use. So remember with integration, you pretty much have your constant rule, your power rule, your trig and exponent rules, and then you have the substitution. So let's talk about this substitution. So here's your first example. You've got sine x e to the cosine x dx. Now, if we were looking at this from a derivative standpoint, you would say, oh, well, we have a product rule with a chain rule, but we don't have that here. You could try to just play some guess and check games. For instance, you could say we could make a guess, and we could say we think that our big f of x, we talked about this in the last unit, that would be my antiderivative, would be equal to, let's just try e to the cosine of x. That would probably be my most obvious one as I'm guessing here. Okay, so now if you take the derivative of that, so if I differentiate f of x, we would get, this would be a chain rule, so leave the e to the cosine of x, because my outside function is at cosine, or e, so that stays the same, times the derivative of cosine. The derivative of cosine is negative sine x, so I believe that if I had just made this negative originally, and this would be negative, that would be the positive, and that would give you f to the beginning there. So it looks like my big f of x is negative e to the cosine of x. Now we can't just guess and check on everything, so there should be a method to help us get there. So here's your method. It's called substitution. The first thing you're going to do is you're going to take, and you need to find a u. Yes, it's very, very similar to chain rule. We're going to go back to working with u's. So your u's are usually in denominators, in exponents. It could be something in a set of parentheses. So I'm going to guess that my u is cosine of x. Now I'm going to differentiate this with respect to x, so du dx. The derivative of cosine is negative sine of x. Well, that's looking a little familiar. Now I'm going to do one other thing. I'm going to move this dx up to the end of the sine x there. So I'm going to have du is equal to negative sine of x times dx. And the last thing I'm going to do, and then hopefully this will become a little bit more obvious to you, is any constants, I'm going to move over to the other side. So usually you divide, but here I'm just going to multiply both sides by negative. So it gives me negative du is equal to sine x dx. Now, if you look over here at this integral, let me just rewrite that really quick for you. This would be the same thing as e to the cosine of x times sine x dx. So all I did was a little commutative property and moved that sine x so that it was next to the dx. Now why did I do that? Because then over here I have that sine x dx is really equal to a negative du. So now I'm going to have e. Now if you remember correctly, u was cosine of x, so e to the u, and sine x dx is negative du. Or better yet, negative e to the u du. Now that is a super easy antiderivative to take because we know the derivative of e to the u is e to the u, so therefore the antiderivative of e to the u is e to the u. So I would get negative e to the u plus c, and then what we're going to do is we are going to plug in for my u, because if you start in x's, you should end in x's. So negative e to the cosine of x, and that was because u was cosine of x. Now, if you remember correctly, that was the guess that we made in the beginning. That was my antiderivative, negative e to the cosine of x. Okay, so now, formal steps, here they are. The first thing you want to do is you want to find your u, and you want to differentiate your u with respect to x, both sides of the equation. Solve for du by moving the dx over to the other side. Move your constant multipliers by division. Substitute into the original integral. Integrate that, and then substitute back in for u. Next question, there's two here. Okay, so again, first step is to find your u. Now, u should be in radicals, in parentheses, in denominators, in exponents. So I'm guessing my u is 5 plus 2x to the third power. Then we're going to differentiate u with respect to x. So du over dx is going to be equal to 6x squared. Move the dx, so du is equal to 6x squared dx. Move the constant over. So therefore, I have 1/6 du equals dx. Now, if you look over here, I'm sorry, made a mistake there. 1/6 du equals x squared dx. Okay, now rewriting this integral using commutative property, and also that square root there can be 1/2, so u to the 1/2, which is the same thing as the square root of u. I guess I'm doing 2 steps here and plus square. 2 steps. Okay, so we're going to have the integral of the square root of 5 plus 2x to the third times x squared dx. So we're ready to make our substitution here. We know that this would be the same thing as the square root of u, because u is 5 plus 2x to the third, and then x squared dx is equal to 1/6 du. Bring your constant out to the outside. Over here. So we'll have 1/6 times the integral. Now I'm going to rewrite that as u to the 1/2 power times du. Okay, now we're going to use our power rule. So we've got 1/6, this constant multiplier comes along for the right. I'm going to add 1 to my exponent, so it becomes u to the 3/2. A half plus 1 is 3/2. And then I can divide by 3/2, or that's the same as multiplying by 2/3 plus c. Cleaning that up a little bit, we get what, 1/9? Instead of a u, I have 5 plus 2x to the third to the 3/2 plus c. And that's your answer. Okay, cotangent. We know nothing about cotangents. You would think it would be easy. It's not as easy as you would think, but I bet we could start by writing this as the integral of, let's see, tangent is sine over cosine, so cotangent is cosine cosine of 7x divided by sine of 7x. And that's because tangent is sine over cosine, so cotangent is cosine over sine. So you could try your u to be 7x, but it's not going to help things to simplify at all. So what I'm going to do is I'm going to try my u to be sine of 7x. Now the reason why I chose sine is because it's in the denominator. So usually your u's are in your denominators, in the exponents, underneath radicals. Okay, so step one, find your u. Now sometimes you pick the wrong u. Just try a different one. Du, the derivative of sine of 7x. This will be a chain rule question. So the derivative of sine is cosine of 7x times 7 times the derivative of the inside there. So derivative of the outside at the inside times the derivative of the inside. Yes, you can do another u substitution for derivative, but it's just a lot. Okay, so then I'm going to do two steps here in one, because hopefully you're getting familiar with this. I'm going to move the 7 over. So 1/7 du, and I'm also going to move the dx up, is equal to cosine of 7x dx. And looking over here, if you notice, there's my cosine 7x dx. So I'm going to be left with the integral cosine 7x dx is 1/7 du all over, and then sine 7x was my u. So cleaning that up, I bring the 1/7 to the outside. I'm going to write this as 1 over u du. This is one of our rules that's actually natural log, absolute value. So that will be equal to 1/7, the natural log of the absolute value of u plus c. Substituting in for u, you get 1/7 natural log absolute value of sine 7x plus c. And yes, it is the natural log of the absolute value. You can't take the natural log of a negative number. And there's your answer. Okay, so we're getting really close. I think we just have just these two examples right here. So this one right here, let's see here, what should be my u? It looks like secant is in parentheses, because back in the day secant squared, but I think I actually want my u to be tangent of x. Okay, why is u equal to tangent of x? Well, what's the derivative of tangent? The derivative of tangent is secant squared x. Moving that du dx up, du is equal to secant squared x dx. And if you notice, that's that portion right there. Okay, so we're going to rewrite this integral. The integral, tangent of x is my u, secant squared x dx is du. Okay, now this one is slightly different because it has bounds. So if you notice, you have a 0 and you have a pi over 3. So this is interesting. So right now, these are x bounds. We don't want them to be x bounds because we're in terms of u. So what we want to do is transform them into u's. And what we have is that u is equal to tangent of x. So my upper bound, u, will be equal to tangent of pi over 3. And my lower bound will be tangent of 0. Well, tangent of 0 is easy. That's just 0. So that's going to stay like that. Now, tangent of pi over 3. I think I may have noticed this page not being blank. So quick unit circle. It's horrible because it's not centered. Yeah. Okay, so that point right there is 1, 0. And this point up here is 0, 1. And remember, I showed you this trick before. Where you have everything is of the form radical over 2. So this one is technically radical 4 over 2, which means this is radical 3 over 2, radical 2 over 2, and radical 1 over 2. And then the other ones are just opposite of that. So this would be radical 2 over 2. radical 2 over 2. This would become a radical 1 over 2. And this up here would be radical 1 over 2, comma, radical 3 over 2. So this one goes radical 4, radical 3, radical 2, radical 1, 0, and then the other one counts down to 0. Okay, so now we want tangent of pi over 3. So pi over 3 would be this one right here. That would be, that's a horrible color, sorry about that. That would be my pi over 3. Because remember, there's pi over 6 down here, pi over 4, and then pi over 3. So pi over 3, tangent is sine over cosine. So it'll be radical 3 over 2. That's your sine. Cosine is radical 1 over 2. That gives me that. Those cancel. That is radical 3. So that gives me my upper bound of radical 3. Okay, so now we have a super easy antiderivative to take because it's just u. So we're going to have u squared over 2 because you add 1 and divide by the new exponent. And we're going to evaluate that from 0 to radical 3 using that fundamental theorem of calculus. So we'll have f of radical 3 minus f of 0. And that will give me radical 3 squared over 2 minus 0 squared over 2, which gives me 3/2. And that will be your answer. Okay, one last one to try. One last one. So same thing as before. Look for your u first. So my u will probably be x squared minus 4. So du will be equal to 2x. Move everything around. So we're going to have 1/2 du is equal to x dx. So now I'm going to do my substitution here. So I'm going to have the integral. There's my x dx. So that'll be equal to 1/2 du. And then on the bottom, I have my u, which is x squared minus 4. Again, my bounds are x bounds. These are equal to x, but I need them in terms of u. And remember, your u is x squared minus 4. So my upper bound will be 1 squared minus 4. My lower bound will be 0 squared minus 4, which will be negative 3 and negative 4. So negative 4 and negative 3. Now I'm going to clean this up a little bit. I'm going to bring the 1/2 to the outside of the integral. That is from negative 4 to negative 3. And I'm going to leave that as 1 over u du. Integrating that, I'm going to have 1/2 times the natural log absolute value of u. And then because I have bounds, I need to evaluate them from negative 4 to negative 3. So I need to do f of negative 3 minus f of negative 4, which will give me 1/2 natural log absolute value of negative 3 is 3 minus 1/2 natural log absolute value of negative 4 is 4. Now, if you remember from last year, if you're ready for a little bit of log review, we will then have 1/2 whenever you, because I just factored out that 1/2, then I have natural log of 3 minus natural log of 4, and that is division. So I'd have the natural log of 3 divided by 4. If you really want to know, we'd have the natural log of 3/4 to the 1/2 power. And I think I'd probably leave right there. But sometimes with multiple choice, you may just want to look at your log rules really quick. So hopefully, after that video, you will be somewhat comfortable in evaluating integrals using a substitution method. There's your steps one more time. you find your U, you differentiate your U with respect to x. Yes, you're differentiating while integrating, so it's super fun. You solve for du, you move your constant multipliers, you substitute, you integrate, and then you substitute for u. So we really only have one extra thing left to learn. That's your separation of variables, and that will be